All right, my friends, we have come to that time that we all dread, and that is the time when we have to use math in ecology. Okay? The way we are using math in ecology is to study and model population growth. Okay? Okay? Um, Populations, if you'll recall, is a single species. A population is a single species of organism that lives in a particular environment, not a huge, but a particular place, and they interbreed and they interact with each other. Okay. Now, as an ecologist, it's important to be able to, if you are studying an ecosystem, to monitor population growth of a particular group. Is the population growing? Is it exploding? Is it declining? Is it disappearing? What's happening to each population in your ecosystem? It's a valuable thing to be able to study. So it's also valuable to be able to take what we know about a population and perhaps hypothesize where that population is headed based on what we know in terms of its current numbers and what it's done in the recent past. So we have equations that allow us to model or hypothesize, if you will, what a particular population might do in the future if we know what it's done recently. So let's get to some basic things. Of course, we know that populations of organisms grow and decline over time. You may have a lot of organisms be born in your population and the number goes up, or they a lot die, a lot go down, the number goes down, whatever. It's important as ecologists to be able to predict and analyze these changes, and sadly for some of us, math is a tool we can use to do that. Now, this is all very elementary here, but make sure we're comfortable. Things that can affect population growth, population size over time, are new organisms being born. Please remember this is referred to as natality. Okay? Existing members of the population may die, which is going to bring your population size down. Please note that this is called mortality. Okay? New organisms can immigrate or come into the population from a neighboring area, or organisms that are actually in your population may emigrate or leave. If I were you to distinguish these two terms, I would remember that this E in emigrate is the same E that begins the word exit. Okay? Now, for our purposes, as we analyze population growth, okay, we are going to ignore immigration and emigration. So I'm drawing a line through those. We're going to ignore those and just focus on births and deaths. Okay? So that's done. Now, the basic concept mathematically about population growth is that if you are observing a population over the course of a year, some time interval, so we're going to call it usually a year, we may call it a month or whatever. If we see that the population at the end is not the same as the population number was at the beginning, that's going to be a change in the population side, which will be determined by how many members of your population are born, subtracting from that how many die during that interval. So the change in population, so if we went from 100 to 200 over a year's time, then that extra 100, so the change in population size here would be we increased by 100. That would be determined by calculating how many had been born and how many had died over the course of the year. Okay? So there is a basic way to express that mathematically. All right? And again, let's not get all freaked out. Remember that delta is the symbol for change in, so the change in n, where n is simply the population size you have. If I started with 100, okay, and then went to 200, okay, then delta N is 100. That's how much it changed over time. And then delta T is time. That's the change. So that is a 1 year time period. All right. B simply equals the number born over that time interval. D equals the number that died during that time interval. Okay. That is a straightforward equation. Okay. So the change in how many you have in the population over the change in time equals the births minus the deaths. Okay. Now, however, as ecologists, what we are especially interested in is expressing this births and deaths as the average number of births and deaths per individual during that time period. So if I had a change in my population size of 100, it grew 100 organisms, I want to know as an ecologist, on average, how many new organisms, or how many organisms did that change per individual, okay? So what we are calling this is the per capita birth rate and the per capita death rate. How many deaths per individual, how many births per individual in the population. Per capita birth rate is as lowercase b. Per capita death rate is symbolized as lowercase m. Now, so this means that, on average, maybe 2 organisms were born per individual that originally existed in that population. And on average, maybe 1 individual died per individual in that population, or something like that. I don't believe that would mathematically work. But on average, how many deaths occurred per individual, how many births occurred per individual. Okay? Now, this is important because we can use this idea of per capita birth and death rates, B and M, to calculate how many we expect per year to be born or to die in a population of any size. So this is going to allow us to model, to predict, to hypothesize what we expect for an upcoming year. Okay? So if you know your per capita birth rate, B, and you know the current population size, okay, what you have, then the equation number of births, big B, equals per capita birth rate times the number you have will tell you how many births you might expect in the upcoming year, assuming that's your time frame. Same goes for deaths. So you can use this little equation to tell you how many you would expect to die, how many actual individuals you would expect to die over the coming year, okay? So that's helpful in making predictions, okay? So, therefore, since this is true, I'm going to slip back up here for a minute. Since B, number of births, equals little b times n, and D equals little m times n, then we can rewrite this equation. If you'll remember, I'm going to scoot back up here. We said that basic population growth concept can be written like this. The change in number over time equals B minus D. Well, since B equals little b times n and D equals little m times n, then we can simply write this equation like this, okay? So that's a new way to write the equation. We're stepping towards some equations that should be able to help us calculate some important values. So we're stepping towards that. Now, given that this is true, and we've established about per capita birth rate and per capita death rate, ecologists are most interested in the difference between B and M. Is your birth rate higher than your death rate? Is your death rate higher than your birth rate? Or are they the same? They are interested in the difference between the per capita birth rate and the per capita death rate. Why? Because that's basically going to tell you, in a very quick, easy, numerical way, is your population growing or is it declining? Now, little r is the symbol for the difference between these two. So little r equals b minus m, and this is the difference between the birth and death rates, per capita birth and death rates, and it is called the per capita rate of increase. This is little r. This is the value we are interested in. It's the difference between these two rates. If the R value can tell you a whole lot. If your R is greater than 0, then that population is going up. If it is less than 0, then the population is going down. If it equals 0, then your population is experiencing no population growth, zero population growth, or ZPG. It is flat, it is stable, okay? This doesn't mean if R equals 0 that there are no births and deaths. It just means they perfectly counterbalance each other. Little r can tell us a whole lot in a very quick snapshot about that population. And we can also write it, since little r is b minus m, we can write this as the change over time in number of the population is equal to this difference between b and m times the number we have in the population. Okay? Now, this is not hard. Now, real ecologists express this using differential calculus. I never sat in a calculus class in my life. I bet you can believe that. Because they do use differential calculus, we write it like this. Notice it is the same equation. All we have done is replace the delta with the little d. It works the same way for us. It makes no difference as far as we are concerned. It's just if you see it, it's going to be expressed in that way. All right? So please do not get hung up on that. Just pretend it's a delta and we'll all be fine. All right? Now, we have talked about two types of growth: exponential growth and logistic growth in your podcasts, okay? Please remember that exponential growth, if this is time and this is number of organisms, exponential growth, we see this J curve where we get slow growth in the beginning, but then it shoots up dramatically, okay? It assumes ideal conditions for the population in question. They have abundant food, they have no limitations at all. They are free to reproduce as fast as they can reproduce to their physiological capacity. Now, under such conditions, we assume that the per capita rate of increase, the little r, is the maximum rate possible for the species because it's ideal conditions. So they're just going to reproduce as fast as they can. So this maximum rate possible for the species, known as the intrinsic rate of increase, is labeled as R max. So we just add a little max to the R. So this is saying we're reproducing as fast as we can, all right, for this particular organism, for this particular species, okay? So now, all we've done is altered to tell us what exponential growth is going to be, okay, in the population. We've just said that instead of just any old R, we're going to put in the maximum rate of growth possible for this species, okay? And that is our equation that will help us work with exponential growth modeling, okay? Now, there's another type of growth called logistic growth. And in this case, in logistic growth, we have, again, time, we have number of organisms, but this time our population is going to slowly increase, then rapidly increase, but it is then going to level out. And the reason the growth is going to level out is because we are going to hit carrying capacity. There is a limitation on growth. There is a limited amount of food or a limited amount of space in the environment, and that is as many organisms as that environment can sustain, okay? Now, in order to model populations experiencing logistic growth, okay, you just have to add in a piece of the equation to take into account this concept of reaching carrying capacity, or K. K is the maximum number of individuals the population in the environment can support, okay? So that will take our equation and make it look like this. Please note, all of this is exponential growth from here over. This part of the equation here is simply saying we are going to now plug in this idea of carrying capacity, and that is going to affect our population as well. You can't just grow unlimited forever, okay? Now, that is some basic background on these equations. What I've given you in class are some problems. I think one of the problems also has to do with population density that I have not gone over, but it's pretty straightforward. You just doing a calculation regarding how many organisms per unit space, basically, and that's not too difficult. If you have trouble with that, we can talk about it in class. Okay, so work with this, try to do the problems based on what I've shown you here, and then please bring your questions back with you to class, okay, and we'll work on it. Thanks for watching. I will catch you soon. Take care.